So hello everybody. Today we're going to be doing a lab on latent heat, and specifically what we're trying to measure with the experiment that I'm going to show you today is the latent heat of fusion of water. So in other words, how much energy does it take to melt 1 kilogram of water? That is exactly the number that we're going to try to measure today. And the way we're going to do it is using something called a calorimeter. So this is a calorimeter right here. Let me show you the different components of it. The first thing we should note is that there are two cups. We have a small inner cup and we have a larger outer cup. And separating those two cups is a ring, and it prevents them from making contact, and basically this ring is made of an insulating material. It prevents heat from flowing from the inside to the outside. Okay? Another way we insulate the calorimeter and prevent heat flow is with this rubber lid, which can be placed on top like this. So you notice how there's this little stirring rod that's sticking out. Okay, we use this just to stir the contents of the cup around and make sure that heat gets distributed evenly. That's what that's for. And the last thing to note here is that we can put a temperature probe to monitor the temperature of what's inside this cup through this little hole in the top. Okay, just like that. So those are the components, and in a nutshell, what this allows us to do is to maintain insulation between what's in this inner cup and the outside. Okay? There's basically nothing but air between these two cups, and air is a really terrible conductor of heat. So while we're doing our experiments, the assumption is going to be that no heat is flowing from the inside of this cup to the outside. Okay, that's going to be a really important assumption that we make in this experiment. Alright, so the first piece of data that we're going to take in today's lab is the mass of this inner cup, which is made out of aluminum, and this stirring rod, which is also made out of aluminum. What is their combined mass? We'll use this triple beam balance to see what that is. So, looks like it's somewhere between 80 and 90 grams, because 80 is not enough to tip the scale, but 90 tips the scale, so it's somewhere in between there. And we can kind of fine tune that a little bit more by sliding this piece over a little bit. And to balance the scale, it looks like we have 85.4 grams. Okay, so the mass of your inner cup and your stirring rod together is 85.4 grams. Okay, so here's the next part. I have prepared here some water. It's a little bit hotter than tap water. Basically, I combined some tap water with boiling hot water, and this is at about 30 degrees Celsius, which is what we want for this experiment. So what I'm going to do is take 150 milliliters of this water and put it into our calorimeter cup like this. So it's about 150 milliliters. And the next thing we want to do is find the mass. Okay, so in particular, I'm going to take the combined mass of the stirring rod, the inner cup, and the water that's now inside, and we're just going to find the combined mass of all that using the triple beam balance just like before. So if you remember, when we just had the stirring rod and the aluminum cup alone, that was about 84 grams, and I added 150 milliliters of water to that. Water has a density of about, of exactly 150 grams per milliliter. So I can expect to just add 150 to what we got before, and that should be our mass measurement for this. But let's actually measure it. So I'm going to put this around 235-ish or 234-ish. And looks like we're not quite balancing the scale. Okay, there we go. Okay, so it looks like to balance the scale, we have 239.3 grams. All right, so here's the next part of our experiment. I'm going to take the calorimeter cup that we've prepared, and I'm going to put that inside the larger outer cup like this. And then what I'm going to do is I'm going to take the temperature probe, put it through the top of the lid like this, and then have our stirring rod also up through the top of the lid like this so I can actually access it and stir things around. Next, I'm going to take an ice cube and place it in the calorimeter cup, and we'll be monitoring the temperature the whole time. That's the idea. So I'm actually going to hit start on the computer so we can begin taking measurements of the temperature. So now that that's going, I'm going to take an ice cube, okay, get all that excess water on the outside off of it, and then drop that into the calorimeter cup and then start stirring. So the more that I stir, the faster it will melt and the quicker we'll reach thermal equilibrium. Okay, so I'm going to just do this for a while. And then I want to show you what's going on our computer screen here. This graph is showing you on the vertical axis what the temperature of the inside of our cup is. So you see it started around 30 degrees Celsius, but it's been dropping significantly since then. On the horizontal axis, we have time. And I'm going to let this run for 300 seconds, and then we'll see what the final temperature is. All right, so this has been running long enough to see the temperature stabilize. Basically, the temperature has not changed in the last couple minutes, so we know we've reached equilibrium. So there are two things I want to show you. First is, what was our initial temperature starting off? So I can actually read this straight off the graph or from this data table here. So initially, the temperature we were reading was 28.5 degrees. That was before I threw the ice cube in the cup. We have 28.5 degrees. And if I scroll all the way to the bottom, or just read a data point off of the right side of the graph here, we'll see that the final temperature was 21.1 degrees Celsius. Okay, so we have an initial temperature of 28.5 degrees Celsius and a final temperature of 21.1 degrees Celsius. That's going to be our temperature data. And then the last measurement we need to take before we have all the data we need is, what is the mass of this cup with the water and melted ice cube now inside, plus the stirring rod, at the end of the experiment? So basically this way we can figure out what the mass of that ice cube I threw in there was initially. That's what this is for. So let's use the triple beam balance once again. We see that in order to balance the scale, we have a mass of, let's move that a little bit more. That's better. So it's about 251.9 grams. Okay, so that's the combined mass again of the melted ice cube, the original water we had inside, the cup itself, and the stirring rod. 251.9 grams. Okay, so I've basically shown you all of the data collection that goes on in this experiment. Based on the numbers that we've measured in this video, you should be able to calculate the latent heat of fusion of ice. Now, one really important thing to keep in mind when you do your calculations is this. When we think of the ice, the original water that was inside of the cup, and the stirring rod together as a system, this is a very well insulated system. In other words, there is almost no heat flowing in or out. And what I want you to do for your calculations is assume that the heat flowing in or out of this system while the experiment was going on is exactly equal to zero. That's the assumption you're going to make. The heat for this system is exactly equal to zero. If you start from there, you should be able to calculate the latent heat of fusion for water. That's the idea. So the last thing we're going to do is simply repeat the experiment 2 more times. So we'll have a total of 3 trials for the experiment. For each one of these at home, you're going to be calculating the latent heat of fusion. And then in the end, we're going to compare these calculations to the accepted value that we've seen in class. Okay? So that's for you to do at home, and I'll see you in the next lab video.